In this part of the video, we are going to calculate the total energy, mainly the potential and kinetic energy of a sound wave, as well as the intensity of the sound wave. Okay. If you remember, in the last part of the video, the differential equation of sound wave was written as del 2 eta by del x square is equal to, if you remember, 1 by is equal to 1 by c square del 2 1 by c square del 2 eta divided by del t square. Okay, so this is a typical wave equation, and its solution can be written as a function of time and position, right? In the very first class, I have discussed that this solution can be written as eta is equal to eta m exponential I omega t minus kx, or even one can write eta m exponential I kx minus omega t. Okay? You can use both the notation. I mean, if you take the real part of this expression, then you will get the familiar, I mean, eta m cos omega t minus kx, or kx minus omega t. For example, the real part of eta is equal to eta m cos omega t minus kx. Okay, this is the familiar part. I mean, we have discussed about real part of the solution in the last time. Okay, here eta represent the displacement of an air coulomb. Okay. Okay. Now from this expression, we are going to derive certain quantity. For example, we can find out the value of particle velocity, then volume strain, and also we can find out the value of the excess pressure existing inside a sound wave. Okay. Now you see, for the energy purpose, I am going to use the real part of eta, and for determining the value of velocity, particle velocity, or the volume strain, or the excess pressure, I am going to use the complex notation. There are certain advantages of complex notation which you will see as I advance through the derivation of this part. Okay, so we know that particle displacement eta is equal to eta m exponential I omega t minus kx. Therefore, if we have to find the particle velocity will be how much? Particle velocity, say Vp is equal to eta dot. That means del eta by del t. Okay, so this value will be equal to eta m exponential I kx minus omega. Let me write omega t minus kx. Okay, so I have to differentiate this bracketed quantity with respect to dt. So it will be basically d by dt. Let me first do it once so that it becomes clear. Omega t minus kx. Okay, so this value will be equal to eta m exponential I omega t minus kx. Okay, and this will be equal to I into omega. Okay, so I omega into eta m exponential I omega t minus kx. Okay, so this factor we can write this as eta. Therefore, the particle velocity eta dot is equal to I omega into eta. Okay, now probably you understand what is the advantage of writing it in the complex notation, because you can see eta dot is equal to I multiplied by displacement. Here eta is the displacement, eta dot is equal to the rate of change of displacement, that is the velocity or particle velocity. So if you multiply by eta, if you multiply eta by I, if you remember the complex number, when you multiply a number by I or by the imaginary number, there is a 90-degree positive phase shift. Okay, that probably you would remember from your complex algebra class. So now if I plot eta along the x-axis, then eta dot, the particle velocity, will be at a phase angle pi by 2 with respect to eta. Okay, and it is leading, the phase velocity is leading the particle displacement, because there is a phase difference of positive pi by 2 between the particle velocity and the displacement. So this is the advantage of writing this expression in a complex notation. Okay, so first we get the quantity particle velocity. Next we are going to determine what is the value of volume strain, because these are very important quantity in terms of sound wave. Okay, so volume strain, if you remember, volume strain, if you remember, it was represented by delta, and its value is small v divided by v naught, where delta v is small v is the change of volume, and capital V naught was the initial volume. Okay, and in the last part of the video you could have seen that this quantity is written as del eta divided by del x. The value of volume strain is equal to del eta by del x. Okay, so now we are going to differentiate eta with respect to x. Eta m exponential I omega t minus kx. Okay, so if we do it again, the differentiate with respect to x, then what we will find, eta m minus I into k exponential I omega t minus kx. This expression you will find. So basically it is minus ik into eta. So delta is nothing but minus ik into eta. Now you can see what is the advantage of again using this complex notation. Here the displacement is multiplied by minus I. That means there is a phase shift of pi by 2 in the negative direction. That means the displacement is leading now the volume strain. Okay, when a sound wave propagates, there will be particle velocity as well as the volume strain, as well as there will be excess pressure. Okay, now we know that the particle velocity is leading the displacement by a phase angle pi by 2. From this expression we know that the volume strain will lagging behind the displacement by similar kind of phase angle. Okay, so if we plot it here, then if eta is along the positive x-axis, then here particle velocity eta dot, and here will be the volume strain delta. Okay, so we know that volume strain is lagging behind the particle velocity by a phase angle pi by 2. Okay, now third part was our this excess pressure, because when a sound wave travel, therefore the pressure across the air column should be more than the atmospheric pressure. Otherwise it is not possible for the sound wave to travel through the air column. Okay, so if you remember, we have written the bulk modulus of air column mass BA is equal to minus the rate change of pressure in divided by volume strain, del V over V, del V over V. Here V was the initial volume, and del V is the change of volume, and delta P is the the excess pressure. That means how much pressure is greater than the atmospheric pressure. We have denoted it by the quantity small p. Okay, small p del V over V. Okay, so we can write P is equal to minus del V by V into BA. Okay, and del V by V, V is the initial volume, del V is the change of volume. This is nothing but delta. Therefore, we can write minus delta into BA. Okay, and delta value what we have got, minus I k eta into BA. Okay, so into there is another minus, therefore it will be minus I k BA into eta. Okay, so excess pressure is I multiplied by eta into some constant k into BA. These are bulk modulus, and k is the wave number. So basically eta is multiplied by I, the imaginary number. So there will be a phase difference between excess pressure and the displacement, and this phase difference is pi by 2. Okay, so if I again do the plot of phase difference, then if the displacement is along x-axis, then we know that eta dot is having a phase difference of pi by 2 leading the displacement, and also the excess pressure is now leading the displacement, and the volume strain is lagging behind the displacement. This angle is pi by 2 and also this angle is pi by 2. Okay, so using the complex notation, that is the advantage. We can actually find out what is the phase difference between the displacement and other quantities like excess pressure or volume strain, as well as the particle velocity. Okay, so if we consider this expression exponential eta m exponential I omega t minus kx, this is actually representing a sound wave traveling in the positive x direction. This is positive x direction. If you take it as kx minus omega t, then what it will represent? It will represent a sound wave propagating in the negative x direction. So whatever the phase difference we have found here will be opposite when the sound wave propagate in the negative x direction. So what we have found that when the sound wave propagate in the positive x direction, the excess pressure and particle velocity will lead the particle displacement by phase angle pi by 2, and here the volume strain will lagging behind the displacement by phase angle pi by 2. Okay, and if the wave travel in the opposite direction, what we will find that the particle velocity and pressure will lagging behind the particle displacement, while the volume strain will leading behind the volume strain will then now leading against the particle displacement. So completely opposite kind of phase shift will obtain if we consider whether the wave travel in the positive x direction and whether the wave travel in the negative x direction. So you have to keep remember that thing. Okay, so once we have calculated all these quantities, now what we are going to do, we are going to calculate the first, we want to calculate first the kinetic energy of the air column. Okay, if you remember, when it was our we have considered an air column of thickness delta x. Okay, and this was the air column. We have considered a part delta x, and the area of cross section was a, and what we have considered, the density of the air column is rho naught. Okay, now due to the propagation of sound wave, we have seen that this air column will get displaced, and the arbitrary value of the displacement in the x direction was given by the letter eta. I mean, if you remember, I have already told you all these things. Now, if we consider the kinetic energy of the air column of this part, I mean, you see its area of cross section A, and its thickness is delta x, therefore, and its density is rho naught. Okay, so if we consider the mass of this air column, then its mass will be mass of the air column. It will be m is equal to rho naught into v, density into volume. Okay, so rho naught, then volume is equal to a into delta x. Okay, this is the mass of the air column. Here what we are going to calculate, the kinetic energy of the air column. Okay, this thing we are going to calculate now. Okay, so this is the mass of the air column. Now the kinetic energy of this air column, kinetic energy of the air column is given by half into mass is equal to how much? Rho naught a into delta x, and its velocity is eta dot. Eta dot represent the velocity. So half m into v square. So half rho naught a delta x into eta dot square. Okay. Now since we are considering the kinetic energy, so it's a real quantity. So basically what we are going to take an eta we will express the we are going to take the real part of eta in this expression. Okay. So real part of eta was how much? Real part of eta m cos omega t minus kx. Okay, it was the real part of it. Okay, so eta dot will be equal to eta m sine omega t minus kx okay, into omega, and there will be a minus sign, because if you differentiate cos, it will become minus sign. Okay, so it will be minus eta m omega sine omega t minus kx. Okay, therefore kinetic energy of this air coulomb, kinetic energy of the air coulomb, what will be its value? Half rho naught a into delta x, that is the volume, and eta dot is equal to eta m square into omega square sine square omega t minus kx. Okay, this is the value. Okay, and if we are interested in the kinetic energy density, basically what we have to do, we have to divide the kinetic energy by the volume of this element. Okay, so if we want to replace this quantity a into delta x, we are going to find out the kinetic energy density. Therefore kinetic energy density will be equal to total kinetic energy divided by a into delta x, because a into delta x is equal to volume. Therefore something divided by volume, per unit volume is nothing but the density. Okay, so kinetic energy density will be equal to half rho naught eta m square into omega square sine square omega t minus kx. This value we have obtained. Okay, so you see the kinetic energy density is basically a sinusoidal function. Okay, sine square omega t minus kx is there. It's a sinusoidal function, but since there is square only, therefore we have to take only the positive part of the sinusoidal function. If sine kx minus omega t is like that, then if sine square omega t, it will be just the positive part. Okay, so what we are going to what we are interested here is to find out the average value of the kinetic energy density, because nobody is interested about the time variation of the kinetic energy. When we measure the energy of a wave, it is the average value of the energy, time average basically. Okay, so here we are going to find out what is the average value of kinetic energy density. Okay, so if we write it as E average, or basically it's kinetic energy, average value of the kinetic energy density. E average here density, just remember. So basically what we have to do, we have to take the time average of this quantity. So what will be that value? Half rho naught into eta m square. Okay, so time period is how much? 0 to 2 dt, because one whole time period we have to take the if we want to take the average, so we have to take divided it by the whole time period. Okay, so 0 to t, this value will be equal to sine square omega t minus kx into dt. Okay, sorry, this small t, 0 to t. Okay, so half rho naught eta m square 1 by t, and this value will be equal to half into 1 minus 2 cos omega t minus kx. Okay, into dt. Okay, so basically we are going to put the integration 0 to t dt. Okay, so if we do it, half rho eta m square 1 by t, so this value will be equal to half into dt 0 to t minus, this is a, you see, cos omega t is a the periodic function. So if you take the value of the periodic function from 0 to t, its integration is always going to throw up 0. I mean, you can find it for any periodic function, this statement is true. So therefore for a total time period, whether it is sine, cos, then doesn't matter, its always value will be equal to 0. Okay, and you don't have to basically worry what is there in the argument. I mean, whatever the argument, as long as it's a periodic, its value will be always 0. So I'm not going to repeat it. So this value you can find it as 0. Okay, so this value rho naught eta m square 1 by t into half into t. Okay, so dt cancel out, So finally what we will get, 1 by 4 rho naught eta m square. I think there was a omega square. Okay, I forgot that quantity, omega square. Omega square, let's put it here. Omega square into omega square. So this is the value of the average omega square into eta m square. Okay, this is the value of the average energy density. Average energy density, average kinetic energy density, Okay. And this value is half rho naught omega square into eta m square. Eta m is, as you know, the displacement. Eta is equal to eta m into some cos something. So eta m basically means the amplitude of the sound wave. Therefore, kinetic energy depends on the amplitude of the sound wave, its frequency, as well as the density of the air coulomb. Okay, so these three parameters will basically determine what is the average kinetic energy of the sound wave in that medium. Okay, in the next part I am going to determine the value of the potential energy, and the total energy is the sum of the kinetic energy plus potential energy. Okay, so next part what I am going to determine the potential energy of the air coulomb as the sound wave propagate through it. Okay, so see you in the next part.